Two F-117s are approaching their target over Baghdad. Below the cloud cover, radar-guided surface-to-air missiles scan the sky for signs of an imminent threat, but see little more than a small blip that fades into the background of noise. The payload bay doors open, revealing two GPS-guided bombs, destined for the assumed location of the then Iraq president, Saddam Hussein. This simple act may well have revealed the stealthy aircraft to radar below. Its exterior was molded by precise mathematical equations, every facet designed to disperse and absorb the electromagnetic energy surrounding the skies around them. With the bombs delivered and their location potentially given away, the defenseless planes quickly turned to escape enemy airspace. This was a highly specialized aircraft, designed to carry just two bombs in its payload bay, a plane that looked like a fighter jet, but if it met enemy fighters, the subsonic plane, armed with bombs meant for ground targets, stood little chance. It relied entirely on stealth to get behind enemy lines and strike without being seen. Something it did time after time during the Gulf War, striking 1,600 high-value targets without losing a single aircraft. The design began as a simple diamond that aerodynamicists of Lockheed's Skunk Works dubbed the Hopeless Diamond, a template for stealth, a shape that the famous former Skunk Works leader Kelly Johnson doubted would ever be able to fly. Turning this concept into a functional aircraft would take the very best aerodynamicists, propulsion engineers, structural engineers, and radar specialists that Skunk Works had to offer. They carefully chipped away at this simple but revolutionary shape to form a masterpiece. This is the insane engineering of the F-117 Nighthawk. The F-117 Nighthawk's journey began here, on the desk of Ben Rich, the newly appointed director of Skunk Works, taking over from the eminent Kelly Johnson. This paper, a Russian scientific paper translated by the Air Force's Foreign Technology Division, held the key to a new generation of aircraft. War is an ever-evolving game of cat and mouse, and in the past decade, aircraft had switched roles from predator to prey. The development of Soviet radar-guided missiles caught the US industrial machine by surprise, a sudden realization during the Yom Kippur War of 1973. Israeli pilots armed with the latest and greatest American attack aircraft lost 109 planes over just 18 days. These planes were mostly shot down by Soviet-supplied surface-to-air missiles supplied to the Egyptian and Syrian armies. These crews required a fraction of the training that was required to train a fighter pilot, and the systems themselves were vastly cheaper. The Russians had invested billions into the development of radar-guided surface-to-air missiles like the SA-5. These missiles could reach 125,000 feet in altitude and could even be armed with nuclear warheads to blast would-be raiders out of the sky. The extreme altitude would mean Russians on the ground would be shielded from the heat and shockwaves, and the strong winds of the upper atmosphere would carry the fallout to Western Europe. The effectiveness of these missiles was not down to speculation. The balance of the battlefield had shifted towards the Soviets. Air Force planners extrapolated these attrition rates out to a full war with the Soviets in Eastern Europe, and they saw the writing on the wall. The Soviets would wipe out the entire US Air Force in just 17 days. Two strategies to counter this advancement emerged. Conventional wisdom of the time pointed towards designing a plane specifically designed to hug the terrain, to be able to fly long-range missions at extremely low altitude, hiding from radar in the ground clutter. This resulted in the B-1 Lancer. Its variable sweep wing allowed it to tailor its aerodynamics for both low-speed, low-altitude flight and high-speed, high-altitude flight. However, that wisdom would soon be challenged thanks to one brilliant scientist, Dennis Ovelhauser, who, on one fateful day, placed this paper on the desk of Ben Rich, a long, technical document full of complicated equations and theories, but for Dennis, Skunk Works radar dome expert, it held a treasure. The key to unlocking a new way of designing aircraft, a method to calculate the diffraction of electromagnetic waves. Stealth design was not a new concept. The SR-71's first flight predates the first day of development of the F-117 by over 10 years, and it incorporated some early concepts for stealth that were largely based around the laws of physical optics, reflection and refraction. Avoiding corner reflectors was a known method to reduce radar signature long before the F-117 was theorized. What this paper unlocked was much more complicated, once thought to be too complicated to solve: diffraction. Imagine waves approaching a harbour breakwater. It's designed to shield the boats inside from the energy of the sea. With just the laws of reflection, the boats should be completely unaware of the presence of waves outside these walls. And yet, through diffraction, the waves find their way inside. This is a messy, chaotic problem with too many variables to consider for simple analysis, and it only gets more complicated with electromagnetic waves. But this paper, unbeknownst to the Soviets, who allowed it to be published internationally, held the key to the technology that would allow aircraft to become the top predator once again. Ben Rich, the newly appointed leader of Skunkworks, under pressure to take the reins from Kelly Johnson, approved a computer program to be developed. And within 3 months, a working program that allowed simple shapes to be analysed was created, dubbed Echo 1, allowing them to theorize the hopeless diamond. This was, of course, not a plane. It lacked everything a plane needs to fly. It had no control surfaces, no propulsion, no payload. It even lacked a wing. Dennis was not an aerodynamicist. He was Skunkworks' radome specialist, designing the nose cones that housed their plane's radar. This design was a template that could be molded by the most skilled sculptors in aviation. Step 1 was to figure out its mission profile. This would decide several things: max payload, range, and propulsion. With stealth a priority, the F-117 could not have external hardpoints. This was going to limit its weapons capacity. It would feature 2 internal weapons bays, and the plane would be a precision bomber. Its weapon of choice were laser-guided bombs. Inside the nose of the aircraft hid a steerable turret containing a dual field of view infrared sensor, while a second infrared sensor was located to the right of the nose wheel well. And both sensors came with a laser which could be aimed at the target to guide the bomb with extreme precision. The sensors locked onto and tracked targets with help from the internal navigation system, switching from the forward-looking to the downward-looking systems as it passed over the target. These systems were, of course, heavily weather-dependent, as the plane could not guide the bombs through cloud cover, but GPS-guided bombs were also an option. These were the only weapons on board. The plane would be completely defenseless to aerial threats and would thus rely completely on stealth. And because of this, the F-117 was going to be a subsonic plane. Producing a sonic boom was a good way to be detected not by radar, but just any person in the general vicinity. Higher speeds also results in increased aerodynamic heating that could allow the plane to be targeted by infrared guided systems, so the engines didn't need afterburners or specialized engine inlets to slow down supersonic airflow. This simplified engine selection, and the General Electric J85 was selected for the Have Blue demonstrator, which would later be upgraded to the General Electric F404 from the FA-18 Hornet, an affordable, reliable, and maintainable engine. Next, the engine air inlet needed to take shape. Here, things get particularly unique to the F-117. Radar bouncing around inside an engine inlet is like a person shouting into a massive cave. The engine inlet would need to take the same facet angles as the rest of the plane, and so the engine inlet was covered with a radar reflecting grid. The grid had spacing of just 1.5 centimeters. This spacing was key to preventing the transmission of radar. The passage of any wavelength larger than the gaps in the mesh would be impeded. Some wavelengths will still get through, but the inside of the inlet was also lined with radar-absorbing material, or RAM, which covered the entire surface of the aircraft. We don't typically see covers on engine inlets for several incredibly important reasons. Number 1, it reduces pressure recovery. Pressure recovery is the ratio of the average total pressure at the exit of the inlet to the total average pressure in the free stream air. The absolute maximum value is 1, where no pressure is lost and therefore no energy is lost. This is a way to assess the performance of the engine inlet. Having a mesh blocking a large portion of the inlet drastically reduces the pressure recovery and reduces the thrust the engine can produce as a result. Secondary intake doors located here could open at lower power settings to increase airflow, but opening these up during flight was not an option. They were controlled automatically, programmed to open when the plane's speed was below Mach 0.5, and the doors closed gradually as the plane accelerated. This was also how the crew accessed the engine to maintain it, since the front intake was completely covered. This grid created another, much larger problem. During flight, ice can build up on the aircraft. Smaller devices like the airspeed pitot tubes have heating elements and water drains inside them to prevent this critical sensor from being blocked. To prevent this from happening to the inlet grid, the plane came with in-flight anti-icing equipment, with what was essentially a windscreen wiper. A wiper would emerge from the lip below the inlet and spray a glycol-based anti-icing mixture. Next, the engine outlet had to be molded into shape. And once again, the F-117 has an incredibly unique design. The engineers wanted to minimize the heat signature of the plane as well as the radar signature. To do this, they needed to cool the exhaust and distribute it over a wider area so it could mix with ambient temperature air quicker. The exhaust outlet transitioned from a round duct at the turbine exhaust to a flat 17:1 rectangular shaped duct. The duct was also divided horizontally into smaller ducted channels. Below the exhaust, the fuselage extended out with a slight upwards angle into what was dubbed the platypus tail. This shape spreads the heat from the exhaust over a larger area, allowing it to mix with ambient air and cool down faster. The extension was also covered in heat-absorbing ceramic tiles that were cooled continually by bypass air coming from around the engines. This exhaust setup did, however, cause some instability issues that were only discovered during the HAV-Blue demonstration test flights. The thrust of these engine nozzles were angled inwards towards the centerline of the aircraft. However, the angle of this thrust vector was often not symmetric. The thrust angle between each exhaust could differ by as much as 8 degrees in some flight conditions, resulting in differential thrust that could push the plane sideways. The angle was affected by engine power, angle of attack, speed, but in particular, side slip. Side slip is when the relative wind striking the plane does not match the direction of travel, which can often happen on takeoff and landings with a side wind. This became a problem for the HAV-Blue test flights because the flight computer was using a lateral accelerometer to measure side slip. But this asymmetric thrust was pushing the plane sideways, causing the accelerometer to detect side slip. The flight computer then tried to correct for side slip, which did not actually exist, and created actual side slip, which increased the asymmetric thrust, which increased the false side slip signal, a positive feedback loop of instability. This problem was fixed by taking actual side slip measurements using a beta vane. Beta is just the aeronautical engineering term for side slip. With the engine selected and payload capacity determined, the wings needed to be sized and designed. An aerodynamicist has a lot of things to consider when designing a wing: the sweep angle, the aerofoil design, the dihedral angle, and the wing area. Usually these decisions are made based on the plane's main responsibilities. An airliner selects a wing that operates most efficiently at its expected cruise altitude and speed. A fighter plane like the F-16 will be designed to maximize maneuverability and high angle of attack lift. However, the F-117 engineers had their hands tied with many of the choices they could typically make. The sweep angle, which describes the backwards angling of wings, was largely out of their control. Sweep angle is usually determined by the speed of the aircraft. Slower civilian aircraft like Cessnas have no need for sweep as they don't travel even remotely close to supersonic speeds. An airliner's wing is angled backwards to increase critical Mach number. This is the speed at which supersonic flow begins to appear over the wings. Angling the wings backwards allows airliners to fly faster before this becomes an issue. The 787 has a sweep angle of 32 degrees. Supersonic planes, like jet fighters, have their sweep angle determined by speed too, but this time, it's to avoid the oblique shockwaves emanating from the nose and body of the plane from intersecting with their wings, which would cause a large amount of drag and loss of lift. An F-16 has a sweep angle of 40 degrees. Even the fastest planes, like the SR-71, had a sweep angle of just 53 degrees. The Have Blue demonstrator aircraft had a sweep angle of 72.5 degrees, and the F-117 was going to be a subsonic plane, flying at similar speeds to an airliner. A sweep of 32 degrees or so would have sufficed. This extreme sweep angle was being driven by its stealth requirements, determined by the Echo 1 program, and this came with troublesome consequences. A swept wing produces less lift than an equivalent unswept wing. This was made even worse by the rigid design requirements of stealth on the aerofoil itself. The airfoil of the F-117 was composed of simple, flat faceted shapes too, 3 on top and 2 on the bottom. If we map the pressure distribution of a regular airfoil, it may look something like this, while the faceted shape looks like this, with peaks occurring at the facet lines. This resulted in low lift-to-drag ratios and caused issues with aerodynamic flutter, where the wing would vibrate and damage itself. With the reduced lift caused by the sweep angle, in addition to these suboptimal aerofoils, the wings had to be quite large to produce enough lift. The designers increased the wing area with extensions here. This increased the F-117's wing area to 72 meters squared, a massive area for such a light plane. The F-117 had a max takeoff weight of 23,800 kilograms. Compare that to an F-15. The F-15 was designed with a low wing loading in mind, meaning a low ratio of weight to wing area. And yet, the F-15 had a smaller wing area and a higher max takeoff weight than the F-117. The F-15 could simply produce more lift with less wing area. Designing a plane around these flat, faceted sheets was a huge challenge, not just in lift, but in stability too. The massive 72.5 degree sweep in the Have Blue demonstrator caused a pitch instability. If the plane pitched to an angle of attack greater than 17 degrees, the plane would not be able to pitch down again, as the elevons also lost control authority as the angle of attack increased. A concerning pitch instability that required the flight control computer to intervene on the pilot's behalf with a specialized control surface. The Have Blue turned the platypus tail extension into a flight control surface. It automatically deflected downwards when an angle of attack of 13 degrees was exceeded. But this too brought with it some unforeseen issues, which ended the test flight career of Bill Parks, when the control surface automatically deployed just 1 meter off the runway and slammed the aircraft into the ground, bending the landing gear and forcing the pilot to eject. This platypus tail was removed for the final F-117 design. The F-117 was different from Have Blue in several ways. Besides being much larger, the inward-canted, all-movable fins of the Have Blue was switched to a V-tail, and the fins themselves were enlarged to increase control authority. These inward-canted fins matched the 30-degree contours of the fuselage. They served as both the rudder and elevators, a ruddervator. Inward fins like those of the SR-71 and outward canted fins like those of the F-35 work in the same way, and we can see how by examining the resultant force generated when the control surfaces are actuated to different positions. We can actuate them in opposite directions to generate a horizontal resultant force, providing yaw control as a vertical rudder would. Or we can deflect them in the same direction to provide pitch control, as the horizontal elevator would. However, the inward canted fins of the Have Blue were being shielded from airflow by the fuselage during high angle of attack maneuvers, reducing their power to control the plane as they were receiving less air to create lift. The larger outward canted fins of the F-117 helped increase their control authority. The platypus tail was removed, but the F-117 gained a second outboard elevon, where the Have Blue had just one elevon on each wing. These huge full-span elevons were sized to provide more control in pitch. The 72.5 degree wing sweep was also reduced to 67.5 degrees. While still an extremely high wing sweep for a subsonic plane, this 5-degree decrease helped increase the lift of the wing and reduce the pitch instabilities the Have Blue demonstrator experienced. With two large elevons, the F-117's V-tail no longer had to control both pitch and yaw. It was dedicated to just yaw control. Having a control surface like this performing double duty can cause issues. If the plane needs to control both pitch and yaw at the same time, the flight computer has to figure out how to manage the competing control inputs into a single control surface. It's far from ideal. It also increases redundancy in the event of a failure, a much better design than the Have-Blue demonstrator, both of which were destroyed in crashes. With the extremely poor lift-to-drag ratio of the F-117, its maximum takeoff weight was limited. Fuel tanks were located above and behind the main weapons bay, with additional storage in the wings, for a total fuel capacity of 8.2 metric tons of JP-8 fuel, giving the plane a range of 1,720 kilometers. To reach enemy territory, the plane needed frequent aerial refueling. The original trip from Langley Air Force Base to Saudi Arabia for Operation Desert Storm took 15 hours and required 7 refuelings along the way. Air-to-air refueling receptacles were mounted in the upper fuselage and rotated into position. With the plane's poor low-speed flight characteristics, it stood little chance of taking off and landing on aircraft carriers. Lockheed did in fact propose a carrier version of the Nighthawk, the F-117N, which added a tailhook, lowered the wing sweep, added an all-moving horizontal stabilizer, increased power with a larger afterburning engine, and increased payload capacity with more hardpoints. The proposal was rejected, however. The F-117 was a moment of inspired brilliance that the United States Air Force ultimately knew would have a limited shelf life. They kept it under wraps for as long as possible to maintain its advantage, but once its adversaries knew of its existence, counter-strategies began to be developed. Taking the simple template of stealth and trying to adapt it for the next generation of multi-role fighters was never going to work, the worst of both worlds. Ultimately, an entirely new generation of aircraft were needed. During Desert Storm, the Air Force based 36 F-117s in Saudi Arabia, and they only needed refueling tankers as support. These planes operated over heavily contested airspace with impunity. On the first night of their deployment, they struck 26 high-value targets, many of which included the country's surface-to-air missile defense systems. The F-117s were so effective that the Iraqi air defense system was powerless to stop them. What was once a Soviet trump card was rendered useless. Not a single F-117 was lost. This infographic was produced by the Air Force after Desert Storm to illustrate the value of this new technology, estimating the 20-year cost of procurement and operation of this precision and stealth doctrine at $1.5 billion. The standard package of aircraft needed before stealth was developed was much more costly, requiring specialized bombers, fighter escorts to protect them, electronic jamming aircraft to suppress air defenses, and a much larger fleet of refueling tankers to support all of them, costing $6.5 billion. However, the Air Force was well aware this golden period of stealth was going to be short-lived. With its existence known, it was only a matter of time until the enemy developed strategies and technologies to counter stealth. A large part of the F-117's mission planning revolved around knowing the positions and types of radar systems in enemy airspace, and planning a route through them that kept the plane out of range. The first and only F-117 was shot down over Serbia in 1999. Here, a tactic was used that involved moving radar and missile launchers regularly and only turning them on for a short period of time so their positions could not be tracked, making it impossible to plan a route around them. This tactic allowed them to successfully lock onto the F-117 and destroy it. The pilot was rescued, but the military made no attempt to destroy the plane wreckage. At this point, the F-22 had already made its first flight, developed with the very latest in stealth technology while being a true fighter aircraft, capable of defending itself and incorporating even more advanced technology that the public are likely still not aware of. Today, the F-35 employs an entirely new doctrine of interconnected battlefield information, a hive mind of stealth aircraft swapping information between each other. The F-117 was the first true stealth aircraft, but as stealth technology has advanced, stealth is not something expected as a specialization, but is expected as standard. With modern technology, targets can be hit from mind-boggling ranges. The key to survival is to strike before you are seen. The B-2 Spirit was the next rung on this evolutionary ladder, and it was one of the most sophisticated and expensive planes ever produced. We don't have a video on the B-2 Spirit, but our friends over at Mustard do, and it's available exclusively on Nebula. The 20-minute video is beautifully animated and tells the story of how the B2 came into existence. Before I go into an entire spiel about how great Nebula is, I know many of you are sick of signing up for yet another subscription service. So, if you simply want to support our channel and get lifelong access to all of Nebula's exclusive programming, we are offering lifetime memberships for a limited time for $300. Unlike other subscriptions, you can buy once and never pay again. This helps fund original programming like our 5-part Battle of Britain series, where we recreated the central command room of the Battle of Britain to show you in intricate detail how Britain won their most impactful victory. We show you how incoming raids were plotted on the huge central map with color-coded tiles, and how the commander kept track of what squadrons were available using a light-up board mounted on the walls. We spent over a month recreating this room using archived footage and photos for reference, an investment of time for a single animation asset that we simply can't afford on YouTube. For less than the price of a cup of coffee per month, you can get access to all of Nebula's originals, along with our entire catalogue without any ads. You can also easily download videos to watch on the go for just $2.50 a month. This channel depends on the funding Nebula provides us. If you've been subscribed to this channel for more than 3 years, you've seen the huge increases in production quality that Nebula has facilitated, growing from 2D animations that myself and Mike taught ourselves how to do, to having a full team of incredibly talented 3D artists that rival any TV production. This is expensive work, and we would love to grow our team even more, something we can only do with your support, as YouTube ad revenue simply does not cover the bills. Last year, we actually made a small financial loss for 3 months in a row. YouTube is simply a volatile platform where we depend on the whims of advertisers. Nebula is a life raft in a volatile sea of social media. This is a common theme across YouTube creators. We created Nebula to enable and level up our entire roster of creators, to remove the financial uncertainty that forces us to rush projects, to remove the algorithms that force us to analyze data points instead of what really matters, the audience on the other side of the screen. So, if you want to check out all of the fascinating, exclusive content on Nebula, go to nebula.tv/real-engineering or click the link in the description to get 40% off our yearly subscription today for the incredibly low price of $2.50 a month for the whole year.